In this video, we're looking at the relationship between histograms and density curves, because going forward in the course, we're going to be using density curves much more often. So what I want to do here is show you how we essentially build a density curve from a histogram, because that's essentially what a density curve is. It started out as a histogram, and we transformed it so that it became a density curve. So I want to walk through that process in this video. So let's say, for example, that we're looking at the population of San Francisco by age. So we have all of the citizens of San Francisco. There's between 800 and 900,000 of them. And we've graphed them in a histogram by their age. So everyone between age 0 and age 9 is represented in this bar. Everyone between age 10 and 19 is in this bar. Everyone from 20 to 29 years old is in this bar, etc., all the way up to the oldest people in the group, who are 100 to 109 years old. And this histogram, and we know it's a histogram instead of a bar graph because we've grouped the ages into buckets of a decade each, or 10 years each. This first bar represents 10 years, the second bar represents 10 years, the third bar represents 10 years. So we have equally sized groups, and therefore this is a histogram instead of just a bar graph. Each bar here is population in thousands, and so if we put in our vertical axis, this is in thousands here. So this is 200,000 people, 150,000 people, 100,000 people, etc. So what we could say is that all of the people ages 20 to 29, maybe there are, 80,000 or so of them, versus there are just over 150,000 30 to 39-year-olds. So this is our histogram, and it's important to know that we also call this a frequency histogram. So histogram and frequency histogram are more or less synonyms because each bar in our histogram really shows the frequency at which that value occurs. So what is the frequency at which 30 to 39-year-olds occur in our data? Well, about 150,000 or so are ages 30 to 39. So this is a histogram. It's also called a frequency histogram. Now, from here, we can change this into what's called a relative frequency histogram just by changing the vertical axis. So here's what we would do. We would take the number of people represented in each bar, and we would divide that by the total number of people represented in the histogram. So for example, let's say people ages 80 to 89, there are just over 50,000 of them, but let's just say that there are 50,000. So there are 50,000 80 to 89-year-olds. And we know that this chart represents a total of 865,000 people. So if we divide 50,000 by 865,000, so 865,000, we get approximately 0.06 or 6%. So about 6% of the total population are people ages 80 to 89. And what we would do is we would go through for each bar and perform that same calculation. So for example, the 30 to 39-year-olds, there's about 150,000 of them. So we'd take 150,000 divided by 865,000, and we would get a percentage just like we did for the 80 to 89-year-olds. After we have a percentage for every interval, then to turn this into a relative frequency histogram, we just swap out the vertical axis. So our vertical axis here goes away. We change it out for this one. So what you notice here is that we have a value of 0.05. Well, that's the same as 5%, so we could also write this 5%. 0.1 is 10%, 0.15 is 15%, and 0.2 is 20%. So what the vertical axis is allowing us to see then is that instead of knowing that there are about 150,000 30 to 39-year-olds, now our vertical axis allows us to quickly see that about 15% of our total population are 30 to 39-year-olds, or just over 5%, about 6%, are 80 to 89-year-olds. So it just changes the axis so that we're seeing, instead of the actual number of people, we're seeing the percentage of the total data set. So you can see here that 40 to 49-year-olds, they make up the largest group in our population. Since this line is 15% and this line is 20%, they're maybe at about 17%. So the largest group in our data set only makes up 17% of the total data. All of the other groups are some smaller percentage than that. So here about 15% of the data is in 30 to 39-year-olds. Maybe about 13% or so is 60 to 69-year-olds, 12% maybe is 50 to 59-year-olds, etc. So it just lets us see the data in a different way. When you have these percentages here as the vertical axis, that's what makes this a relative frequency histogram. Now, if we show this as a line graph instead of as a bar graph, in order to turn it into a line graph, all we need to do is plot a point at the top of each bar. So we plot a point at the top center of each bar, and then we connect each of those points with a straight line like this. Now, if we remove the bars and we just take the line part of the graph and we bring it over into its own graph, this is what's called a frequency polygon. So we'll go ahead and label that. This is called a frequency polygon. It's a polygon because remember, poly means many, so this is a many-sided figure. We have straight sides, so it's a many-sided figure. And the reason a frequency polygon is important is because sometimes if we have, for example, a perfectly triangular frequency polygon or a perfectly rectangular frequency polygon, we can use simple geometry to find the area under the frequency polygon over a certain interval. Now here's where we go from a histogram or a frequency polygon to a density curve. So notice that when we started here with our histogram or a frequency histogram, we were grouping all the people in San Francisco into buckets by decade. So all of the kids under 10, all the kids between 10 and 19, all of the people between 20 and 29, etc. Well, the fewer buckets we use, the more inaccurate our polygon is going to be. If we only used 3 buckets instead of what we have here is 11, if we only use 3 buckets, then our polygon might be really abrupt connecting the tops of those 3 bars. But since we've used 11 buckets, our polygon can follow this a little more closely. The more buckets we use, the more bars we have here, the more closely these straight lines, the more closely our polygon is going to follow the tops of the bars. And you can imagine if this were possible, if we start using more and more and more and more and more bars to show the data in this histogram, then our polygon really starts to smooth out because the distance from one bar to the next is a lot closer. So we're going to get a smoother and smoother curve the more buckets or the more bars that we have. So the idea is that if this were possible and we could use an infinite number of buckets to show our data, our polygon would get totally smooth. And when it's totally smooth, that's when it becomes a density curve. So for this example, and this is totally rough, but the density curve might look something like this. It would follow the data as it goes along and become a smooth curve. And this is the density curve for the data. Once we have the density curve, we can start thinking more clearly about the area under the curve. So for example, if we wanted to know how many people in San Francisco are age 70 or older, so right at about this cutoff right here, everybody 70 or older, we would want to look at the total area that falls under that curve. Because remember, the amount of data will always add up to 1.0 or 100%. Remember before over here we said the 40 to 49-year-olds made up about maybe 17% of the population, and then the 30 to 39-year-olds made up about 15% of the population. Well, if we were to add those all up, so 15 plus 17 is 32, so these two groups together make up 32% of the population. If we add all those bars together, we're going to get to 100%. The whole population is 100% of the population. So then we can say things like, if we want to know the 70-year-olds or older, we can shade in about that area of the density curve. And since we're saying that all of the area under the curve will make up 100% of the population, then we can estimate things like the fact that this area maybe looks like it's approximately 25% maybe of the total area under the curve. I mean, you could say it's a little more, 30% maybe it's less, 20%, since it's just this little tail piece here. But let's just say that this is 25% of the total area under the curve. That tells us that 25% of our population is going to be 70 years or older, because this is the 70 years or older mark in our interval right here. So we would shade in that area, and then based on how much area is there under the curve, that's how we would estimate total percentage of our population.